Hello everybody. In this video, we are going to discuss as elaborately as possible the requirement elicitation step for the ADAS feature blind spot detection. Here we go. For requirement elicitation of blind spot detection and a detailed engineering playbook. Now, what is the purpose of blind spot detection? Blind spot detection requirement elicitation turns the product intention. What is the product intention? To warn the driver of the vehicles in the blind spot and prevent unsafe lane changes. So sometimes you glance in your rear view mirror and you think the road is empty and you try to make a lane change. But after making the lane change, suddenly you realize that there is another vehicle in the lane. It happens to every experienced driver. And to prevent that scenario, blind spot detection feature has been developed. So blind spot elicitation, converts the product intention into complete testable set of requirements thus that drive sensors perception control machine interface safety SOTIF verification and supplier contracts. So these are all the stakeholders: owner of the sensor, owner of the perception software, the control software, the safety engineer, the SOTIF engineer, the verification and validation engineers, and even the suppliers. All right, now below is a step-by-step recipe you can run in the workshop plus concrete copy paste requirement templates and verification guidance. All right, first of all, before we jump into the actual requirement elicitation, let's see elaborately why this step matters for BSD. Okay, BSD means blind spot determination. I'll be using this acronym henceforth. Now BSD sits at human automation boundary and it must be accurate because the drivers have to trust it and timely so that a lane change decision can be corrected and not annoying. It should be low nuisance alerts. If the requirements are vague, you will get either missed detections or too many false alerts. Okay, the too many false alerts will lead to driver disablement or losing trust in this feature. So elicitation forces you to make a detection zone, alert logic, timing, degraded behavior, and acceptance criteria explicit and measurable. So to proceed further, first of all, you have to identify the stakeholders. So when you brainstorm the requirement elicitation for blind spot detection, who are all the stakeholders who are going to put forth their ideas? All right, who should be in the room to answer this simple question? Product owner, system architect, perception lead, the sensor hardware owners like radar owner or camera owner, controls ADAS lead, the human machine interface or user experience lead, the functional safety and SOTIF engineer, the validation ODD analytics, brake electronic stability owner for lane control assist safety interlocks, diagnostic service, homologation, cybersecurity, and also key suppliers like suppliers who supply the short range camera, short range radar, camera, ultrasonic, and field data analytics. Now, talking about the essential outputs from elicitation. All right. So, what are the major deliverables from this elicitation step? The first is blind spot detection operation design domain document, which includes the numeric bins or numeric bifurcations or numeric divisions, systematic software requirements, state machine and HMI specifications, perception key performance index, detection zone geometry, latency budgets. This is important, latency budget, because smaller the latency, the more costly the equipment will become. ICD, signals, rates, timestamps, SOTIF and HARA trace entries, scenario catalog, verification validation plan, plus acceptance criteria, dataset annotation spec, degradation diagnostic service requirements, and traceability matrix in ALM tool. Now, talking about this recommended workflow, usually this takes a 2 to 4 day structure. Day 0, this is a sample thing which I'm offering to you so that you can implement when you are developing this blind spot monitoring or blind spot detection. So, fleet telematics, near misses, competitor specifications, target market regulations, and day 1 ODD plus use cases, day 2 perception KPIs, detection zone geometry, timing budgets, day 3 we can take care of the HMI state machines, escalation ladder, nuisance suppression rules, SOTIF HARA diagnostics, verification validation plan, owners and traceability. Deliver written decisions on owners at the end of each day. All right. So these are the recommended. Okay, this is not mandated. This is recommended workshop flow. Now, first of all, you have to define the blind spot detection, operation, design, domain. For every numeric requirement, attach its ODD. Okay, operation design domain acronym is ODD, and henceforth I'll be using this acronym. So please take care of it. So typical ODD dimensions to make requirements against. There are various speed divisions or speed ranges. First is 0 to 30 km per hour, parking slow urban, 30 to 80 km per hour urban rural, and 80 to 140 km per hour highway. All right. Now road types: multi-lane highways, two-lane rural, urban multi-lane on ramps, off ramps, and parking maneuvers. Now lane geometry, lane width, shoulder presence, curvature limits. And environment conditions include day-night bins. And again, this okay, we'll discuss this in a more elaborate manner. At what lux, at what lux you can call it a day, and at what lux or what brightness level you can call it a night. All these things we'll discuss. Next is rain, light, snow, visibility thresholds, sensor obstruction allowed. So these are all the various conditions that must be clearly defined and considered before we set on this requirement elicitation journey. Cars, vans, trucks, motorcycles, bicycles, specify which classes are in the scope for ODD bin. Now talking about the vehicle state, towing trailer attached, cargo changes, ESC healthy, trailer sway signals, and out of ODD policy. And this is out of ODD policy, but it's the important step. When to de-arm versus operate with reduced authority versus informed driver. So when to de-arm or deactivate this BSD. Sometimes even that decision has to be taken, and even the decision of that particular decision must be considered or included in the ODD policy. Now, let's talk about the functional concept and state machine. So what are the various states and transitions? What are the typical states? First is feature disabled. Even this is a state. Next is standby. This standby means it is armed or activated. Next, you detect. You detect a object in detection zone. Whether and you also detect that there is no lane change intent. There is no intention of changing the lane. All right. And next, you warn, whether visually or haptically or chime. Haptic means sudden jerk of the seat belt or sudden jerk of the seat. These are all falling under the category of haptic. And critical warning, active intervention. If your system supports lane change intervention. And coming to the degraded and fault, sometimes this there can be degradation like the sensor is not working properly or camera is blocked because of some mud splashed onto it. And also it triggers and transitions to write as requirements. So when it comes to arming conditions, minimum max speeds, sensor health flags. Coming to the detection versus warning, when a confirmed detection is in detection zone and lane change intent detected, turn signal or steering torque exceeded threshold, or proceed to warning policy if object rapidly approaching. All right. Now, when it comes to the warning, you when it comes to warning that cancel when object leaves the zone or driver turns away. Okay. So when you have to cancel the warning when the object leaves the blind spot detection zone or driver turns away. Now talking about the overrides, drive steering, brake input threshold or override warning interventions, and inhibitions like reverse gear, towing configuration, trailer attached, and sensor blockage. Now talking about the escalation ladder, examples you should quantify. All right. The first step is passive visual icon when object present in the zone. So when the object is present in the zone, there must be some passive or a mild visual icon. And talking about the flashing icon plus single chime when lane change intent is detected. So as the lane change intent is detected, this slightly escalates into a flashing icon or a single chime. And next step is continuous tone plus haptic seat steering cue if imminent collision ask. If the system supports the active intervention and escalate to control. All right. These are the various types of escalation steps in the escalation ladder. All right. And also this should be quantified. What should be the decibel level of the continuous tone? What should be the frequency of the flashing icon? All these things must be quantified. All right. Now from here, the actual mathematical aspect of uh, the actual mathematic aspect of the blind spot detection starts. So first you have to define the geometry and perception requirements and make this measurable. This is important. You have to make those parameters tangible. You must define the detection zone precisely in the vehicle coordinates and link KPIs to that zone. For example, in a detection zone, the longitudinal relative to ego rear bumper, longitudinal distance relative to ego rear bumper from -1 meter to -20 meter behind. And when it comes to lateral, from 0.5 meter side edge to 3 meter from the vehicle side. So this covers the adjacent lane width plus offset. Next comes the azimuth sector. Azimuth sector means rear lateral quadrant. Rear lateral quadrant define left and right sectors in degrees relative to the vehicle. All right. So when you talk about the longitudinal axis is nothing but the axis along the direction of the road. So in that axis, plus or minus 70 to 135 rear quadrants expressed as a ICD polygon or a parametric box. Talking about the perception KPIs. The probability of detection. All right. So in perception KPIs, I'm giving you examples how to convert to requirements. So when it comes to probability of detection for a vehicle class inside the detection zone, it should be greater than 95%, and this is nominal ODD. And false alarm rate. When it comes to false alarm rate, the false alarm rate should be less than 0.1 events per hour. And talking about the localization accuracy, longitudinal RMSE should be less than or equal to 0.5 meters and lateral RMSE less than or equal to 0.3 meter. Talking about the velocity estimation error, the velocity estimation error should be less than or equal to 0.5 meter per second. Now again, it depends on the car. Okay, for example, if it's an ordinary family car, it can be less than it can be approximately 0.5 meter per second. But if it is some high-end sports car, then this velocity estimation error can change depending on the max velocity of the car, and also minimum detectable size radial RCS. Its state depends on the sensor. All right. So talking about the latency, perception target list update less than 100 milliseconds and end to alert including less than 150 milliseconds. Now tracking lifetime and reacquisition after occlusion. Example, track continuity should be greater than 95% occlusion, less than or and also it should be less than 1 second. So the policy rules, and also you should take into consideration the policy rules that must be that must be considered as requirements. Okay, never forget the fact that we are still in requirement elicitation. Okay, you should never lose the sight of that fact. So still under requirement elicitation, you have to finalize the multi-sensor confirmation thresholds, stationary object handling, parking vehicles beside the lane versus stationary obstacles on the shoulder, and classification priority, bicycle versus motorcycle versus car, and its effect on the alert thresholds. All right. So these are the various classification priorities and how that varies the alert thresholds. Okay. Now let's talk about the alert logic and nuisance suppression, because one side you have to alert, but second side you should not be a nuisance. If you're alerting unnecessarily, you become nuisance. So the perfect trade-off should be achieved. So first step is make the HMI logic measurable. It should be measurable. So and trigger maps examples. First, passive presence, no turn signal, no steering, show dim icon only, no chime. lane change intent, turn signal, or steering torque, it should be greater than tau 1. It can be the value depending upon the steering torque. So many Newton meter. And escalate to visual plus chime. So aggressive lane change, turn signal plus lateral steering torque plus object closure speed, escalate to continuous tone plus haptic. Now talking about the false positive suppression, this is important. False positive suppression. Now, if the object predicted to exit zone before ego vehicle would cross into adjacent lane, do not alert. All right. So there should be a threshold only after which the alert should happen. So the threshold below which, before which alert should not happen is also extremely important. So post alert grace. After an alert, suppress retreat alerts for X seconds unless object leaves and re-enters. All right. Now talking about the quantifying human factors, the time between alert and expected driver reaction. The time to alert must be greater than required reaction time for safe correction. Or understand this. This time to alert must be greater than. Underline this word. Greater than. And allowed nuisance rate, maximum of one nuisance event per n hours of fleet time before design changes are required. So here you have to have a proper threshold of the nuisance alerts. So for n hours, for so many hours, only one nuisance event is allowed. So this kind of decision must be taken. Now talking about the safety and SOTIF. SOTIF means safety of the intended functionality. So you have to identify unknown unsafe scenarios. For example, vehicle in adjacent lane with very low contrast clothing with low sun angles and motor rapidly approaching with small radar RCS. Now require confidence behavior, low confidence degrade to visual only and raise earlier warnings. And talking about the ISO 26262, when it comes to HARA path, conduct HARA, hazard analysis and risk assessment, to determine safety goals to prevent unsafe lane change into occupied adjacent lane. All right, and allocate ASIL and derive technical safety requirements, diagnostics and safe states. Okay, so this conducting the HARA is extremely important so that proper ASIL requirements and technical requirements are determined. So requirements must link each detection early action to safety goals with diagnostic thresholds and diagnostic trouble codes to support the safe transition. All right, now talking about the diagnostics, degradation and service. This is also a part of the requirement. So even while developing the requirement itself, you have to keep in view the various diagnostic requirements. So what are the requirements as far as diagnostics that need to be added? First is which faults case cause features to dearm and required function. So what are the exact faults which may cause the feature to dearm or deactivated? Next is DTCs should be raised. So what are the IDs, what are the severity, what is the log content? This must be determined. Next is in-service check, alignment checks after bumper wheel, change calibration procedure after sensor replacement, camera radar blockage detection rules and user messages. In blind spot detection limited, sensor blocked. So these are the user messages that needs to be articulated. And last but not the least, remote telemetry. What telematics to upload or failed near miss events. All right. So suppose there is a near miss event or a near accident event that has to be recorded or not. That decision must also be identified. All right. So talking about the interfaces and timing. Now, when it comes to talking interfaces and timing, the signals you must define the IDs, the units, the rates, the jitter, the timestamp rules. Now, blind spot detection object list, ID class XYZ, V underscore relative, V underscore rel means relative velocity, covariance, confidence, predicted path, timestamp. And when it comes to BSD status, armed, standby, degraded fault. And when it comes to BSD alert level, none There are 4 levels. First is the none, the passive, the warning, and the critical. And when it comes to the driver intent, these are the various things that need to be considered, whether it is a turn signal taking left or right, or what is the steering torque, lane change request, and BSD health flags and DTC IDs. All right, now talking about the message rates, perception list at the rate of 25, 50, hedge, health 1 hedge, events log on the event. Next, when it comes to time sync, PTP or monotonic timestamps, max drift is allowed. All right, so when it comes to time sync, whether it is a monotonic timestamp or is there some kind of drift allowed, that has to be considered. And talking about the timing budget example, sensor update or pre-processing less than 40 milliseconds. This is called the timing budget example. And this is why I already told at the beginning that latency plays a very important role in determining the budget. Now talking about the perception, classify and track less than 60 milliseconds, decision logic less than 20 milliseconds, HMI activation less than or equal to 10 milliseconds, end-to-end budget 150 milliseconds. All right, so these are all the various kinds of timings that must be clearly determined in a tangible manner as you develop the requirements. Next, talking about the data and the machine learning, if using classification, you have to talk about the coverage quotas. So this much percentage, X percentage of the events in ODD bin. For night division, how many percentage of events? For rainy scenario, how many percentage of events? For highway scenario, how many percentage of events? For urban, for motorcycle fraction, for every coverage you must have a proper ODD bin. And also the class balance. Ensure sufficient motorcycle and bicycle examples. All right. So often under represented. Annotation policy, bounding boxes versus instance polygons, velocity tags, occlusion flags, and viewpoint. Also, the quality assurance gates. What are the quality assurance gates? So, inter-annotator agreement must be greater than a certain percentage. And this is confirmed by sample audits. Now, talking about the model promotion criteria, offline probability of detection, offline failure alarm rate, thresholds mapped on the road proxies before fleet deployment. Okay, so this must be considered under data and machine learning if at all you are using the classification. Now, last but not the least, this is the very important step, verification and validation. Okay, here you have to tie the test to every requirement, and this is where exactly the this step called traceability comes into picture. But of course, I will not go deep into traceability because traceability is a total different topic altogether. Now, when it comes to SIL, software in testing, Monte Carlo test, statistical scenario sampling to explore boundaries and compute or expected frequency alarm rate and probability of detection. Now, when topic of Hill, timing and failure injection, message loss, latency stress. All right, and when it comes to track test, we have spoken about software in loop, we have spoken about hardware in loop. Now we will see in the actual proving ground. So in the proving ground, are we going to use the actual dynamic vehicle? Are we going to use the soft target or a dummy scooter or a dummy bicycle? All these things must be clearly outlined and determined even before we deep dive into the verification and validation. All right, so the scenario catalog must include adjacent lane pass. Okay, as many scenarios as possible must be checked. Adjacent lane pass, parallel driving at similar speed, rapid closing. Rapid closing means adjacent vehicle accelerating or ego deceleration. Lane change cut-in. Adjacent vehicles move into ego lane. Motorcycle in blind spot with low RCS and bicycle in adjacent lane. Bicycle in adjacent lane, especially in the urban scenario. Parking pullout. So naturally parking pullout means it's a slow speed. And when it comes to sun glare, reflection, roadside poles causing false positives. And towing trailer cases. All right. Now, statistical sample size guidance example. To estimate PD is equal to 95% with plus or minus 3% margin at 95% confidence. So use the sample size formula for proportions. All right, formulas like n is equal to z square p into 1 minus p by e square with z is equal to 1.96, p is equal to 0.95, e is equal to 0.03, and finally n is equal to 203 events total roundup. All right, so even if you accept 5% margin, n is equal to 73 events. So this is a statistical formula, and if you must accept even 5% margins, this many events must be outlined. So use this approach to size fleeced validation for ODD bin. Okay. So when you are doing this verification validation on actual track test or actual hill or sill, this money, the number of events that are required is calculated in this method. Now I request all of you to pause the video here and go through this step by step. I will just breeze through this because going through every step will be very cumbersome. First of all, when it comes to example requirement template, the first step is BSD operational speed range. All right. So operation design domain available and armed for ego speeds of 0 to 140 km per hour, behavior tuned in speed bin. And next requirement is it shall be armed when sensors are healthy and ego speed within the ODD. Outside ODD, BSD will be degraded or in off state, or you should inform the driver BSD unavailable. And next, when it comes to zone geometry, the detection zone right side, it covers longitudinally from -1 meter to -20 meter rear to the rear bumper, and laterally from 0.5 meter to 3 meter from vehicle side, represented as ICD polygon, and also left side symmetric. I mean, exact symmetricity on the both the right side and left side must be considered. Next is vehicle detection probability in the BSD zone. Again, in the ODD 60 to 140 km per hour, whether it's a clear weather, it's a lane marked, and for passenger vehicles present in detection zone, the system shall achieve probability detection greater than 95% with false alarm rate of 0.1 events per hour. So this clearly shows the vehicle detection probability. And also for verification, that software into in loop Monte Carlo, you have to run this many scenarios. Target car test n runs, which I showed in the previous step. If you are doing with the instrumented fleet validation with CI plus or minus 3%, requiring 203 qualifying events. CI is a important statistical term. All right. Now here I give a small homework. You do in your do a small search in the Google or wherever you want. CI is a very important statistical term, and I'm sure every mathematics student understands what CI is. Now talking about the next step, alert escalation when lane change event. So I request all of you to go through this paragraph very thoroughly about the lane change event, about the collision probability, about the exact icon chime text. So this is the alert escalation. And next, talking about the degraded operation and DTC. Okay, so whenever there is a degraded operation, immediately the diagnostic logs a DTC and also a freeze frame. All right, so to go through this paragraph in a more elaborate manner. Talking about the BSD ICD signals and timing, the requirement is provide BSD object list at 25 to 50 heads with the fields, including, and when the field should be clearly categorized. What is the ID? What is the class? What is the X coordinate, Y coordinate, relative velocity, the confidence, the timestamp, the jitter, less than 5 milliseconds, and all timestamps in monotonic vehicle time base. Now talking about the acceptance criteria, for a production baseline fleet, false alarm rate shall not exceed zero point 0.1 events per hour. This is something which we touched upon in the previous slides. So false alarm rate must be must be judged depending upon so many false alarm rates per this many fleet hours. All right. Now, what are the various deliverables? So finally, when you shut down or conclude the elicitation, these are the final deliverables. The BSD operational design document, the software, the software state, the state machine, the HMI specification and exact text icons, the perception KPI matrix and latency budget, and ICD and message definitions, scenario catalog mapped to each requirement, SOTIF and HARA mapping entries, dataset and annotation specification, verification validation plan with sample sizes and acceptance gates, and also traceability matrix in ALM. Now again, for identifying the traceability matrix, there are a lot of tools like Doors, Polarian, etc. But very commonly used is ALM. Now talking about the common pitfalls and how to avoid them, you must be very thorough about vague detect reliability. Always attach a PD and FAR and ODD. All right. So there should also be no nuisance budget. Specify FAR nuisance suppression logic. Next is hidden sensor assumptions. So there should never be any kind of convenient assumptions about the field of range or range update rate or calibration tolerance. Talking about the missing lane change intent definition, no degradation policy. All right. Sometimes you miss out this degradation policy. So you have to be very clear about and define exactly what limited means and user messages. Talking about the poor data set coverage, require quotas for motorcycles, bicycles, and low RCS objects. Talking about the no statistical thinking, size on road data for confidence levels. All right. So see the sample size example in the previous slide. One of the previous slides, I clearly discussed about the sample size. So these are the common pitfalls that may happen during the requirement elicitation, and this must be avoided at any cost. All right. So final checklist. First is the ODD defined numeric per speed, detection zone geometry, perception KPI, the state machine and lane change intent object, the HMI icons, the nuisance suppression, the degradation, the ICD signals and timing locked, the dataset quotas, especially when you're talking about the machine learning and artificial intelligence. And talking about the verification validation plan with scenario catalog plus sample sizes created, traceability in ALM and owners assigned. All right. So these are the checklists before freezing the requirements. All right. So with this, I come to the conclusion of this requirement elicitation for blind spot detection. So if you want to learn a comprehensive course about ADAS, Advanced Driver Assistance Systems, you can log into this website, https://sarangatutorials.com, which is my personal website. And in this website, a comprehensive course of 26 chapters and 127 pre-recorded videos are uploaded, which you are most welcome to buy and enroll into. All right, it's a certified course, and by enrolling and getting the certificate, you become a certified ADAS professional. Now this is the sample certificate. All right, and this course is going to educate you about the various subdomains comprised in ADAS and various topics that are needed to work in ADAS seamlessly. This sentence is important. Completion of the course will certainly position you as an accomplished ADAS professional. I repeat, it has totally 26 chapters and 127 pre-recorded videos. All right. So, and moreover, course is a lifetime access course, and you can complete the course at your own pace, time, and convenience. I am attaching the link to this course in the description box, from where you can directly land onto the buying page, from where you can enroll into the course or buy the course. Okay. Thank you. All the best, and thanks for your time again.